Hi guys, welcome to this page of the notes. Welcome to this set of videos. What we're going to do here is talk about symmetry. Does an object have symmetry? And there are two kinds of symmetry. We'll talk about both of those. Before we do that though, our essential question, right? The question we want to be able to answer by the time we get to the end of this set of notes. Does an object, does a figure have a line of symmetry? Or, because it could have both, or rotational symmetry. We'll talk about those. Our objectives, you need to be able to identify lines of symmetry and rotational symmetry. All right, so the things we're going to talk about, the things you'll need to be able to do. Symmetry, super easy. Let's just jump right into it. First of all, a line of symmetry is simply this. A figure has symmetry if a rigid motion exists. A rigid motion exists that maps the figure onto itself. It's as simple as this. Think of taking your figure, your object, if you were to fold it in half, right? Do the two halves lie directly on top of each other? Here's a perfect example. I've given you a triangle right here. Please notice you should be able to just look at it and kind of visualize almost like a butterfly folding its wings up. All I got to do is run a, hold up, that's my highlighter, not what I want. Run a line right down through the center of it right there. If I fold that object across that line, right, the two halves will lie directly on top of each other. That is a line of symmetry. All right, that's what we're looking for. Does an object have a line of symmetry? It's possible for an object to have more than one line of symmetry. Some objects won't have any lines of symmetry. So that's what we're looking for there. Line of symmetry is simply a reflectional line, right? But you're reflecting the object onto itself across that line of reflection, which is why we're talking about lines of symmetry. We just got done talking about reflections a section or two ago. So let's do a couple more here. Lines of reflection. Do we have any? Well, if I take a look at this object, hopefully what you'll recognize is a few lines of reflection for this one. I could simply divide this guy right down the middle vertically right there. That would fold that guy over and it would lie directly on top of each other, but that's not the only one. I have a horizontal line of reflection where I fold the top down onto the bottom and it would lie directly on top of itself. But that's also not all. Please be very careful. Notice if I go diagonally through this guy this direction, or, right, so I take that half and I fold it up, line of symmetry, and another one right here. Count the lines, 1, 2, 3, 4 lines of symmetry in this object. So here's what we've seen. It's possible for an object to have one line of symmetry. It's possible for an object to have more than one line of symmetry. And then we come down to a couple of these guys down here. So here we go, just a few more example problems. Run through it, see if you can find all of the lines of symmetry. All of the lines of symmetry. Well, in this object right here, this parallelogram, take a look at that. Are there ways that we can fold this guy on itself so that the two sides line up? And I see a line of symmetry right there, a vertical line of symmetry. If I were to fold it across that line, right, the two halves would lie directly on top of each other. There is no horizontal line of symmetry. There is no horizontal line of symmetry, so I only have one line of symmetry. Keep going. What about the next one? Well, actually, again, hopefully what you're seeing is that there are several. I could split it there. Fold it, line of symmetry. I could split it right there. Fold it, that's another line of symmetry, but that's not all. I could also do it that direction and in that direction as well. Those are all going to be lines of symmetry, and just like the object right above it, it has 4. Again, remember, a line of symmetry is a line that will reflect the object onto itself, right? If folded across that line of symmetry. The last one, hopefully at this point you're getting real good at recognizing these. I have only one line of symmetry. It is a vertical line of symmetry. There's just one line of symmetry for that object. Okay, so lines of symmetry are simply going to be a line, could be vertical, could be horizontal, could be at an angle, right? Just look for those lines of reflection that would map the image across that line of reflection onto itself. Again, like butterfly wings folding up, they're mirror images of each other on either side. So you're looking for those lines of symmetry. Then what we want to do, our next objective was to go ahead and take a look at rotational symmetry. This is going to be if we rotate the object around the point of rotation, that object will again map directly onto itself. A star is a perfect example of rotational symmetry, right? If I go ahead and take this star and I rotate it 72 degrees, this point will go to here, this point goes 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 to here, and I get the exact same image of the object after that rotation. A star is a great way to look at this. It turns out that this one has 1, 2, 3, 4, 5 points on it. 5 points, right? And so the way that we found 72 degrees is simply this. One full rotation is 360 degrees. Divide 360 degrees by 1, 2, 3, 4. The 5 points on the triangle, you get 72 degrees. So that's how I know rotating this object 72 degrees each time will map the object onto itself. You'll get a star where the point is up, one going left, one going right, and 2 down at the sides at different angles. Okay, so rotational symmetry, is there some way to rotate that object so that it maps itself right back onto the object? Let's practice this a couple of times. Again, right here, that's how you go ahead and find those angles of rotation. So 72, 144, 216, and 288. How did I do that? 72 degrees, that gets point to point, and then 72 plus 72, 144. 144 plus another 72, 216. 216 plus another 72 degrees, 288. All right, so here we go. On this one, this first triangle, is there any way to rotate that triangle to map itself onto its original image, the image onto the pre-image? And there is not. You would have to go a full 360 degrees, which is cheating. Any object will map onto itself if you go 360 degrees, so no rotational symmetry. Right? The only way for this pre-image to then become the image is to go around a full 360 degrees. That doesn't count. But the next one, right? Please notice that this is an equilateral triangle, which means 1, 2, 3 points, right? If I just rotate that guy 3 times, I keep getting it maps itself onto itself. Well, the math here is real easy. 360 degrees divided by 3 is going to put me at, I have rotational symmetry. Yeah, right, I have rotational symmetry, and again here, let me just do this real quick. 360. That goes in 1 time. 1 times 3 is 3. Subtract 0, bring down 2 times. 6, bring down the 0, 0. So 100, every 120 degrees, this object will map onto itself. So that means that my angles of, or my rotational symmetry would be at 120 degrees, then add 120 plus 120, which would be 240, and then 240 plus another 120 gets me to 360, but 360 is cheating. Any object will go around. So there we go, 120, 240, and then again, I can write it, but all the way around is kind of cheating a little bit. Anyway, here we go. The next one. I do have rotational symmetry. You can just look at it and see rotational symmetry. I have 4 points, 360 divided by 4, that's an easy one. Every 90 degrees, every 90-degree rotation maps this image onto itself. So yes, I have rotational symmetry, yes. And that rotational symmetry is going to be at 90 degrees. 180 degrees, that's 90 plus 90. 180 plus 90, 270. All the way back around to the original would be 360. Generally, we don't put 360 though because that's kind of cheating. Every object rotated 360 degrees maps right back to itself. All right, here we go. Last thing we're going to do, just again to really sort of drive this stuff home, I want to know for the following objects, does it have line symmetry? Does it have rotational symmetry? Here we go. I take a look at the first one. Oh, I recognize this from the first page. I know that I have line symmetry right there that'll fold itself over. What about rotational symmetry? Is there any degree of rotation less than 360 that maps this object onto itself? Hopefully you can see the answer is no. You'd have to go all the way around to map this object back to itself. So there is no rotational symmetry, but one line symmetry. Next one. Oh, I do recognize this one from before. There, 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 and there. So we already know this one had 4 line symmetry, 4 lines of symmetry, but also take a look, right? I've got a number of vertices. 1, 2, 3, 4, 5, 6, 7, 8, which means that 360 divided by 8 puts me at 45 degrees. So every 45 degrees, this object is mapped onto itself. Go ahead and take a look at the last one. Hopefully you can see that you have line symmetry, but no rotational symmetry. Guys, that's lines of symmetry. Thanks so much for joining me for this set of notes. I'll see you guys next time.